Pressure measurement. When setting up and evaluating HVAC equipment, we must have ways of measuring air pressure in the system. Pressure measurements can be used to evaluate and improve the effectiveness of an HVAC system. With pressure measurements, we can detect undersized components that will cause restrictions in the airflow, overwork the air handler, and cause excessive noise. Pressure measurements can be used to ensure that airflow is balanced evenly throughout the duct branches and the appropriate amount of air is delivered to each zone. In this unit, we will explain air pressure, describe basic air pressure sensors, and how we measure air pressure in an HVAC system. What is air pressure? Pressure is the force per unit area that a liquid or a gas exerts on a body. For example, in the case of atmospheric pressure, the pressure comes largely from the weight of the air. The air that we live in is much like the ocean. A deep sea diver must don a special suit to descend to great depths, since the deeper you go, the higher the water pressure. Likewise, we live at the bottom of an ocean of air. At lower altitudes, the air pressure is greatest, and at high altitudes, air pressure tapers off. This gaseous sphere surrounding the Earth has a pressure of about 14.7 pounds per square inch at sea level. We don't feel it, however, because our body's internal pressure equals the pressure exerted by the atmosphere. Every object on Earth is affected in this way by atmospheric pressure, including HVAC systems. In order to control temperature and air quality in our environment, an HVAC system makes use of air pressure to circulate warm and cool air throughout a building. It is important to understand how to measure air pressure in order to help design and optimize an HVAC system. Let's look at a few instruments that we use to measure pressure. Measuring air pressure. Consider a simple glass U-tube, commonly referred to as a manometer, partly filled with a liquid, for example mercury, but open at both ends. The only pressure acting on the fluid is atmospheric. Because the atmospheric pressure is equal on both sides, the fluid is not displaced. But if one end of our U-tube is attached to some pressure source, and that pressure is higher than the atmospheric pressure, it'll push the fluid to one side. The difference in fluid levels is proportional to the pressure in the balloon and becomes our means of measuring pressure. We can measure this difference and express the air pressure in the balloon in inches of mercury. This is just one standard unit that is used for pressure measurement. In this example, we measure the pressure in the balloon and find it to be 3 inches of mercury. When measuring pressure, we must use different liquids for high and low pressures. Liquids with higher densities will displace less for a given pressure. Therefore, a liquid such as mercury is better for measuring high pressures, and we would express these measurements in inches of mercury. For better precision at lower pressures, we would fill the manometer with water and express our measurements in inches of water. For the purposes of measuring the relatively low pressures in ductwork, water is more suitable. To gain even more precision, we often make use of a slightly different type of manometer called the inclined manometer. It works more or less the same as the U-tube manometer, but one of the columns is placed at an angle, therefore making the scale easier to read. A water-filled inclined manometer is used to measure very low pressures in HVAC systems. When testing HVAC equipment in a laboratory setting, we make extensive use of inclined manometers to make air pressure measurements. While the manometer may seem a little low-tech, it provides highly reliable, precise, and reproducible measurements. However, due to its size and delicate construction, it may not be the instrument of choice in field testing. Handheld pressure measurement units, such as those shown, might be used instead to calibrate and evaluate HVAC systems in the field. Types of air pressure. When making pressure measurements, it's important to distinguish between absolute and relative pressure. Depending on the instrument and technique used in the measurement, one or the other will be the result. Absolute pressure is a measurement of pressure relative to a vacuum. To make this measurement, you could extract all the air out of a room and measure your pressure source with a U-tube or inclined manometer. Because there is no pressure remaining in the room to act on the opposite side of the manometer would give you an absolute pressure measurement. Alternatively, you could use an instrument such as a barometer. It employs a vacuum-filled canister which deforms proportionately to the pressure that it is exposed to. This deformation is amplified mechanically and shown on a meter face. In either case, because you're comparing the measured pressure to a vacuum, you are measuring an absolute pressure.
Relative pressure is a pressure measurement relative to the surrounding atmosphere. If we use a manometer to measure pressure, the value we measure is the net result of the pressure source countered by the surrounding atmospheric pressure. The difference in fluid levels is therefore the relative pressure. Note that if you know what the atmospheric pressure is at your test site, you can easily convert from relative to absolute pressure by adding this value to your readings. Due to the nature of the way HVAC systems are tested and installed, relative pressure measurements are most relevant and suitable for our needs.
As mentioned before, we experience about 14.7 psi of atmospheric pressure. We refer to this type of pressure as static pressure. When the wind starts to blow, we have to deal with the added force due to the speed of the wind. We call this pressure the velocity pressure. The sum of the static and velocity pressures equals the total pressure. These three types of pressure are associated with HVAC systems as well: static, velocity, and total pressure. Static pressure in an HVAC system is the force required to move air through various components such as filters, dampers, and diffusers. Static pressure is exerted equally in all directions. When we deal with pressure in tables and equations, we often use the notation P sub S to stand for static pressure. Velocity pressure is the force exerted by a moving air stream. It is produced in the direction of the moving air. When we deal with velocity pressure in tables and equations, we often use the notation P sub V. Total pressure is the sum of static and velocity pressure. We use the notation P sub T to stand for total pressure in tables and equations. If we insert a tube into a duct at 90 degrees to the airflow, we can measure the static pressure. Because of this positioning, the velocity pressure has no effect on the pressure measurement. If we insert a tube into the duct facing the airflow, we can measure the total pressure, which is the effect of the static pressure plus the velocity pressure. Again, note that the static and velocity pressure combine to create total pressure. So, to arrive at a measurement of the velocity pressure, we must subtract the static pressure from the total pressure measurement. Pressure measurements are often made with a device called a pitot tube. The pitot tube can be used to measure all three types of pressure depending on how it is connected to an inclined manometer. In this cross-section of a standard pitot tube, we see that it is really two tubes in one and that there are taps that allow us to connect a manometer to either the inner or the outer tube. The outer tube receives its signal from small holes in the tube wall and is exposed to the duct static pressure only. Here we see static pressure measured by the pitot tube. The inner tube receives its signal from the hole facing the airstream and is therefore exposed to the total pressure. Here we see total pressure measured by the pitot tube. As you no doubt recall, the static pressure must be subtracted from the total pressure to determine the velocity pressure. By connecting the static pressure to the low pressure side of the manometer, we counter the effect of the total pressure with the static pressure. In effect, we are subtracting the static pressure from the total pressure using this configuration. The resulting measurement on the inclined manometer is the velocity pressure of the airstream. In practice, the airflow may be very uneven within a duct, especially near a transition. Pressure measurements should be made as far from the transition as possible. 10 duct diameters is recommended. But because this is not always possible, and one can never be sure that a single measurement represents the pressure across the entire cross-section of the duct, it is best to use multiple samples, or a traverse sampling of pressure measurements. For example, in a round duct,
We take samples in an X-shaped pattern such as that shown. We can average these values to arrive at a more accurate measurement. In a functioning HVAC system, we would make use of the Price SP series pressure sensor for measuring air pressure at terminal units. It is superior to the pitot tube in that it automatically receives representative pressure samples from across the cross-section of the duct and automatically averages them. Once we know the velocity pressure, we can use this value to determine the air velocity in feet per minute using this equation. We take the square root of the velocity pressure in inches of water, in this case the square root of 0.77, and multiply it by 4,005 to arrive at an air velocity of 3,514 feet per minute. We can then use this equation to determine how much air is flowing through the duct in cubic feet per minute. In the case of a round duct, the cross-sectional area is pi r squared. The duct in our example has a radius of 4 inches or 0.33 feet, so the cross-sectional area is 0.34 square feet. We multiply this by the air velocity and determine that the airflow is 1,194 cubic feet per minute. Pressure and transitions. What happens to the airstream as it passes through transitions in a duct? One might expect that if we measure the pressure upstream and downstream of an elbow, for example, the static, velocity, and total pressure would be about the same on either side. However, this would only occur if we could construct perfectly frictionless ductwork and transitions. In the real world, all ductwork and transitions present some degree of friction and obstruction. Whenever the airflow is required to change direction, turbulence is produced and there is a loss in total pressure. If we take measurements, we see that the upstream static pressure is 0.75 inches of water and the velocity pressure is 0.25 inches of water for a total pressure of 1 inch of water. On the downstream side of the transition, we measure the static pressure at 0.68 inches of water, the velocity pressure at 0.25 inches of water for a total pressure of 0.93 inches of water. If we compare the total pressure upstream and downstream of the transition, we see that the total pressure loss in this case is 0.07 inches of water. We call this a pressure drop. Note that the velocity pressure is the same upstream and downstream of the transition. In a duct of constant cross-section, the velocity pressure should be the same no matter where you measure it along the length of the duct. However, obstructions and transitions such as elbows will cause a drop in static pressure and therefore in the total pressure. If we examine a simple HVAC system, we will find that the highest total pressure occurs at the air handling unit. This is where the static pressure needed to force air throughout the system is created. As we move downstream, we will see that there is a series of pressure drops across each transition until we get to the diffuser. As air leaves the diffuser, it reaches the same pressure level as the environment. Bernoulli's law states that if we change the velocity of the airstream by passing it into a larger or smaller duct, the resulting change in velocity pressure will be offset by a change in static pressure. If the air passes into a smaller duct, we cause an increase in the velocity pressure and the static pressure will decrease. If the air passes into a larger duct, we cause a decrease in the velocity pressure and the static pressure will increase. In an idealized, frictionless situation, the total pressure should be the same upstream and downstream of these transitions. Whatever is gained or lost in velocity pressure is offset by a change in the static pressure. We use Bernoulli's law to help predict what will happen to pressure at transitions where the cross-section of the ductwork changes. Let's take a look at an example. In this case, the airflow is going from a small duct into a larger duct through a transition. We take a measurement of the static and velocity pressure on the upstream side of the transition and find the static pressure to be 0.75 inches of water and the velocity pressure to be 0.23 inches of water for a total pressure of 0.98 inches of water on the upstream side. As the air enters the larger duct, the velocity of the air decreases. We therefore see a decrease in velocity pressure and an increase in static pressure in accordance with Bernoulli's law. In the absence of duct friction and air turbulence, we might expect to make the following measurements on the downstream side of the transition: a static pressure of 0.91 inches of water plus a velocity pressure of 0.07 inches of water for a total pressure of 0.98 inches of water. What we lost in velocity pressure is gained in static pressure. However, due to turbulence produced at the transition, there will be a loss of total pressure. If we take measurements on the downstream side of the transition, we would more likely see the following measurements: a static pressure of 0.82 inches of water and a velocity pressure of 0.07 inches of water for a total pressure of 0.89 inches of water. We see that there has been a total pressure loss of 0.09 inches of water. In the interest of energy efficiency, we want to deliver air to the environment with the least effort possible. In the best-case scenario, pressure drops in the HVAC system are kept to a minimum. Like all other HVAC components, diffusers should produce very low pressure drops as well. Performance need not be sacrificed to achieve this, since well-designed energy-efficient diffusers, such as Price's SCD line, will still produce optimal air patterns with low pressure drops and low air velocities. Of course, if we measure the pressure outside the diffuser, we will get something close to the environmental pressure, that is to say, a relative pressure of zero. If we compare the pressure found in the neck of the diffuser to the atmospheric pressure, we can determine how much of a pressure drop there is attributable to the diffuser. In our example, we measure the pressure inside the neck of the diffuser and find the static pressure to be 0.06 inches of water, the velocity pressure to be 0.06 inches of water, for a total pressure of 0.12 inches of water. Whatever pressure we measure in the neck of the diffuser represents the pressure drop across the diffuser. In this case, we have a pressure drop of 0.12 inches of water. These are just a few representative transitions commonly found in an HVAC system, and we have seen how each affects air pressure. Whenever airflow is required to change direction, turbulence is produced, and there is a loss in total pressure. We've seen how velocity pressure is transformed into static pressure, and vice versa, as air flows through different sized ducts. And finally, we've looked at the pressure drops created by diffusers. Each and every component must be carefully selected to minimize pressure losses in the HVAC system. In this unit, we've examined the nature of air pressure. Using instruments such as the inclined manometer and pitot tube, we can measure different types of pressure found in an HVAC system. Price engineers use these methods to design and evaluate HVAC components. Acquired pressure and airflow measurements are published in the Price catalog so that you, the HVAC professional, can make informed decisions regarding component selection. We hope that you've enjoyed this overview of pressure measurement. For more information, contact your local Price representative or visit our website at www.price-hvac.com for more information.